So in question 1, we'll have to write this balance symbol equation. So all I'll do is write down the symbols for the substances to start with. So we've got Mg for magnesium, and that's going to react with oxygen. Now remember, oxygen on its own is O2. It's a diatomic element, diatomic molecule, which means two atoms covalently bonded in a molecule. Must put our arrow in, so that's 1 mark. Then on the right hand side it is MgO, because both the magnesium and the oxygen have a valency of 2. That's the second mark. And now that we've got 2 marks, the third mark comes about by balancing it. So on the right hand side we need a 2 in front of the MgO. Remember, when balancing equations, the big numbers have to go in front of the whole formula. But now that has created 2Mg, so we need to go and put a 2 in front of this one. You could have done it slightly differently if I do it under here. So I'm going to do out the original equation unbalanced first of all. You can see that there's 1 magnesium on either side, 2 oxygens on the left, only 1 on the right. So what you could also have done is put a half in front of that, and then that would have made 1 oxygen here and 1 here. On to part B. What's the structure of magnesium? And here, well, magnesium's a metal, and all metals have a metallic lattice. So it doesn't matter if it's magnesium, copper, iron, zinc, all the same structure. And the bonding is also the same, that's metallic. And remember, that's where you have that attraction between the delocalized electrons and the regular lattice of positive ions. Onto the oxygen. It's O2, you can see it has low melting and boiling points. It is a gas. The structure is going to be molecular covalent. Sometimes it's called simple covalent. Then onto magnesium oxide. Well, magnesium's metal, oxygen's a non-metal. This is going to be an ionic compound. So the state at room temperature, before this one you have to think of what are the typical properties of ionic substances. And they are solids at room temperature and pressure. Because they have such a high melting and boiling point, I mean, you can see that here, it doesn't melt until 2852 degrees C. So obviously it's going to be a solid at 25 degrees C. The colour, now you may just remember that magnesium oxide is white. It burns with that bright white light and forms the white solid of magnesium oxide. But you should also remember that this is group 2, and all elements of group 2 form compounds, solid compounds that are white. Doesn't matter what they are. So you could have calcium oxide, that's white. Calcium sulfate, that's white. Magnesium sulfide is white, and so on. So all compounds of groups 1 and 2 form solid compounds that are white. Then on to part 2. Now, if you can't picture this in your head, I would suggest you draw out the molecule of oxygen. So I'm just going to do that now. I'll draw the outer shell. This is a double covalent bond, but there are inner shell electrons as well. So if we have our nucleus, this one will have 2 electrons, and this one will also have 2 electrons. Because it's asking us here to work out the total number. But you can see now that the total number is 8 and 8. That's going to be 16. The number of lone pairs, well, here is a lone pair, so it's 1, 2, 3, 4. Those are just pairs of electrons not involved in bonding. So I'm going to put in 4. And then the number of electrons in covalent bonds, well, you can see there's a total of 4 there. Part 3, explain why oxygen has a low boiling point. Well, oxygen is molecular covalent in its structure. So this oxygen could have been replaced by carbon dioxide, nitrogen, ammonia, methane, etc. It's the same answer that applies to all molecular covalent structures. They all have weak van der Waals forces between molecules that require little energy to break. So hopefully you remember if we have an oxygen molecule and then we have another one, obviously strong covalent bonds between the atoms, but between the molecules there are these weak van der Waals forces, and those are the ones that get broken. For part 4, we have to give a definition of ionic bonding. So all you have to say here is that it's the attraction or the electrostatic attraction between oppositely charged ions. The next question follows on from that. We have to complete a dot and cross diagram to show the electronic configurations of the ions that are formed. The first one is from a magnesium atom. So I'm going to draw my nucleus with the first shell, and then I'm going to do the second shell. I know that the outer shell electrons are going to get lost. Metals lose electrons, non-metals gain electrons. Magnesium will lose these outer 2 electrons, and they will actually get transferred over to the oxygen atom. So the first shell contains 2 electrons. The second shell will contain 8 electrons. So then the charge has to be worked out. Now hopefully you remember that atoms have 0 charge. So this is neutral and this is neutral. And the reason why they're neutral is because they have the same number of protons as electrons. If then the magnesium atom loses 2 electrons, which are negative, then that means it's going to become positive overall because the protons don't change. This will have 12 protons, 12 electrons. They cancel each other out. And if we look at the ion, protons will still be the same, but now the electrons are only 10. So we've got 2 extra positive charges. So that's why the charge will be 2 plus. The formula will therefore be Mg2 plus. We'll do the same sort of thing for the oxygen, but this time the oxygen atom will gain the electrons. So I'm going to draw my nucleus, first, second shell. Now I'm drawing dots this time. So one of the electrons from the magnesium transfers and pairs up with this electron, and then the other electron from magnesium will pair up with this one. The oxygen atom had 8 protons, 8 electrons, which is neutral. Here on the ion, it has 8 protons. Remember, the protons do not change, but now it has 10 electrons. It has gained 2 negative charges. And so the formula of the oxide ion is O2 minus. Notice that the non-metal changes its name to ide. The metal doesn't change. Part C, write a balanced symbol equation for this reaction, which is between magnesium, which reacts with carbon dioxide. So we'll start off with that. We've got magnesium plus CO2, and we're told that magnesium oxide is formed and the other product is carbon. So we're going to get MgO and C. And then just check that this is balanced. Well, there are 2 oxygens here, only 1. So we need to balance these up. So we put a 2 there. And that has now made 2 magnesium, so we need to put a 2 here. You can use multiples for that if you want. The bonding in carbon dioxide molecule, this is one which contains a double covalent bond. The other molecule which has a double covalent bond is oxygen. So make sure you learn those 2. So oxygen, carbon, and the oxygen. There's a double covalent bond there and a double covalent bond there. That's the 4 electrons. If I use X to represent the electrons in the carbon on the outer shell, and then each oxygen has 6 electrons in the outer shell, so I've got 2 already. That means I need another 4, and you can see now that this has 8 electrons in its outer shell. This is 8, and then I just need to complete this oxygen. Question 2, part A. Suggest a reason why Mendeleev placed zinc in the same group as calcium. So calcium and magnesium are in group 2. So think, well, what would be the properties of the metals in group 2? Well, they're going to be very similar in terms of their reactions. So that means that zinc must also have similar chemical reactions to those in group 2. You could say that it forms a 2 plus ion because calcium and magnesium in group 2 also form a 2 plus ion. In part B, then we'll have to describe other features of the periodic table which are different to Mendeleev's table. And the answer should focus on the modern table. Right. So in the modern table, the elements are in order of atomic number. Now, I don't need to say anything about Mendeleev's table, that the elements are in order of increased atomic mass, because we're told here we have to focus on the features of the modern table. The modern table has more elements, which means there are no gaps. The modern table has the noble gas group. Mendeleev's table didn't have that. The modern table also has its transition metal block. And be careful here, don't say that it has transition metals, because Mendeleev's table also contained transition metals. It's just that they weren't sort of separated into a separate block. And then a final thing you could write is that the modern table has the lanthanides and actinides, which weren't present in Mendeleev's table. On to part C, you should have now a periodic table in front of you, and from it you have to choose a metal, a transition metal, which forms a black oxide and a green carbonate. Okay, well, that's going to be copper. You can write the name or the symbol, because the question is just asking you to identify. So it doesn't say name or give the symbol, and when it says identify, you can give name or symbol. On to part 2. The most reactive halogen. Well, halogens, like all non-metals, get more reactive as you go up the group. So that's going to be fluorine. The element in period 4 and group 5, that will be arsenic. Be careful with this type of one. Remember, in your periodic table, you've got hydrogen and you've got helium, and then you go into period 2. A lot of people forget about this first period, and they start counting here, which is wrong. Part 4, the element with atomic number 32, that's going to be germanium. Be careful that you don't say geranium, that's a plant. D part 1, give the name of group 1. That's just simply the alkali metals. Be careful not to say the alkaline metals. 2, complete the balanced symbol equations for these 3 reactions. Well, the first one, metal plus water gives then this metal hydroxide and hydrogen. Hydrogen is going to be H2, and it's obviously a gas. Reaction 2 is a displacement reaction. The chlorine is more reactive than iodine, so it displaces it, and you get potassium chloride and iodine, which is I2. Halogens on their own are diatomic. It's going to be aqueous. So it just follows the pattern here. The final one, silver nitrate, sodium chloride. But basically what happens here is the metals switch places. So we'll get silver chloride and sodium nitrate. Now you need to have a bit extra care with this one, because silver chloride is a solid. So you get a precipitate forming here. Remember, precipitate is a solid that may form on mixing 2 liquids. And anytime you see silver nitrate solution, you should really automatically be thinking, oh, this is testing for a chloride, bromide, or iodide. And this precipitate would be white. Sodium nitrate will be aqueous. Now, even if you didn't remember that, you can look up the solubility rules on the back of your data leaflet, and you'll be able to see then that silver chlorides are solid and sodium salts are soluble. Part 3. Potassium reacts with water. In reaction 1, heat's released. The metal disappears with a crackle. You get a colour solution, and we'll have to give 3 other observations. So make sure you do not give the observations that are stated here. So other observations could be things like a lilac flame, or it moves, it floats. And what else does it do? Fizzes, or you could say bubbles, or gas formed. Remember, fizzes and bubbles, they're the same thing. It gives out a lot of heat, so it does melt to a ball. Part 4, we'll have to give the colour change in reaction 2. Well, potassium salts are colourless in solution. You have to know that. So any compound that's formed from a group 1 metal in solution, always colourless. Doesn't matter what it is. Potassium iodide, sodium chloride, potassium, strontium, fluoride, etc. They're all colourless. Iodine is formed, and iodine is in solution is usually a brown colour. So we can say here colourless to brown. And you may be allowed sort of a variation of brown, because sometimes if there's not much iodine formed, the solution can look yellow. So you probably would be allowed to say yellow as well. And part 5, what is observed in reaction 3? We've already touched on this. This precipitate is white. So here you can just simply say white precipitate. Question 3 then is about acids. The formula of the hydrogen ion, it's simply H+. The ion present in all alkalis, it's like sodium hydroxide, potassium hydroxide. So we'll write hydroxide, OH-. Remember, don't put in OH- here because it's asked for the name. What is meant by a strong acid? That's one which completely ionizes in water. Or you could say dissociates, and instead of water you could say solution. B, part 1. Which one of the solutions would have the highest pH? Well, let's see if we can just eliminate any of these. The highest pH means it's going into more alkaline territories. So if we look through these, that's an acid. Okay, that's an alkali and that's an acid. So the obvious one, the only one there, is going to be D, sodium hydroxide. Which one of the solutions would have the lowest pH? So again, we're going to look for acids. Now we've got acids here, but we can eliminate the ethanoic acid because that's a weak acid. So I know it's not going to be that. And if we compare these two hydrochloric acids, well, this one, C, has a higher concentration. So C would have a lower pH. It's more acidic than B. Okay, so now it's between C and E. And if you look at E, it has a higher concentration again, so it's higher than C. Therefore, the answer, the lowest pH, would be E. The colour when phenolphthalein is added to D, well, D is an alkali, so phenolphthalein would be pink. And then part 4, a balanced symbol equation for the reaction occurring between C, which is hydrochloric acid, and D, which is sodium hydroxide. So this is an acid plus alkali gives us salt, which is sodium chloride, and water. In part C, we've got a flow scheme that shows the production or the formation of magnesium sulfate. And then if we just go on to part 1 for now, write a balanced symbol equation for the reaction of magnesium carbonate with hydrochloric acid. Let's move this up a bit. Magnesium carbonate is MgCO3. Sulfuric H2SO4. That'll give magnesium sulfate. Both the magnesium and the sulfate have a valency of 2. Water, carbon dioxide. That's already balanced. Just as a tip, anytime a carbonate reacts, carbon dioxide will be formed. So always remember that. Definition for part 2 of a salt. So there it is. Some or all of the hydrogen ions in an acid are replaced by metal ions or ammonium ions. And if you're not too sure what ammonium ions are, they're NH4 plus. So for example, if I reacted ammonia with sulfuric acid, I would end up with ammonium sulfate, which would be that. So I've replaced the hydrogens in the sulfuric acid here with ammonium ions. What piece of apparatus is used to measure 25 centimeters cubed? Well, that's going to be a measuring cylinder. I know it's a measuring cylinder because it does just say 25. If it had said 25.0, then I would have to have write a pipette or a burette. Part 4, how do you know that no further reactions occur in step 2? Well, let's have a look at step 2. So the magnesium carbonate has been added to the acid until no reaction. Well, magnesium carbonate produces carbon dioxide gas. That means there will be fizzing. So the reaction will stop whenever the fizzing stops. So there's no more fizzing. Or you could say no more carbonate reacts or no more carbonate disappears. Don't say dissolves. Okay, that's different to disappears. 3 pieces of apparatus required to filter the solution in step 3. Well, filtration, you need filter funnel, filter paper, and some sort of container to collect it in. For example, a conical flask or an evaporating basin. Part 6. Why is the solution heated to half the volume in step 4? So remember, we generally heat the solution to half and then we allow it to cool and crystallize slowly. Well, at this stage, or before this stage, the crystals remain dissolved in the solution because there's a large volume of liquid there. By evaporating off half the water means that we concentrate the solution and the crystals become less soluble. And then for the last part, 2 other methods which could be used to dry the crystals. Well, they're dried here in a low temperature oven. A high temperature can't be used because that would drive out the water of crystallization. So a simple method would be to dry between pieces of filter paper. And must be pieces, or you could say between 2 pieces of filter paper. And the final method would be in a desiccator. In question 4, we'll have to work out the empirical formula of a compound, and the compound is aluminium sulfide. Now, to work out empirical formula, you need to know the number of moles of each element present. So let's start then with part 1, calculating the mass of the sulfur. So let's look at the question. So we're trying to work out the formula of the aluminium compound. 0.81 grams of the aluminium reacted, and it formed 2.09 grams of the sulfide. So that means aluminium sulfide. Therefore, the mass of sulfur, which must have reacted, must be the difference between these two. So we can do 2.09.0.81, and that gives an answer of 1.28. Part 2, work out the number of moles. So we're going to have the mass that has just been worked out divided by the RFM, or the MR, or AR, I should say, of sulfur. And that's 32, which gives 0.04. Part 3, calculate the number of moles of aluminium. Well, the mass was 0.81, so just 0.81 divided by the atomic mass, which is 27, and that gives 0.03. Now you can see here what the ratio is going to be. Again, I'll just do it out like this to make sure you understand. We've got 0.03 of that. Has to be a whole number ratio. You can see it's going to be 3 to 4. It's going to be Al3S4. Now, if you divide it through by the smallest number, which in this case is the 0.03, that would have given a ratio of 1 to 1.33. And when you do this and you get an answer of 0.33 or 0.66, what you've got to do is multiply everything by 3. And so that would have given 3 to 4. So you still end up with the same answer. Part B, we've got this reaction between aluminium oxide and magnesium. And then in part 1, we'll have to fill in the table, or complete the table, the number of moles of magnesium. Well, the formula mass of magnesium is 24. You can see the mass is 288. So we're using these two values. So we just simply divide 288 by 24. And that gives an answer of 12. Okay, which reactant is the limiting reactant? Okay, well, I'm going to put it up here. So we've got 4.5 moles of that and 12 moles of magnesium. I'm going to start with the magnesium. You can see it's a 3 to 1 ratio. Okay, so 3 to 1 ratio. So if we start with 12 moles of magnesium, that means that it will react with 4 moles of aluminium oxide. We simply divide the 12 by 3. Now there are 4.5 moles that are actually reacting, and that's more than the 4. Okay, so if we put it this way, so imagine that's dividing by 3, that would give you 4. So the 4.5 is obviously greater than the 4, so it's more than we need. This is excess. That means the magnesium is a limiting reactant. Now if you start with the aluminium, so let's have a look at this. Let's say you did, okay, aluminium is 4.5, we'll multiply that by 3, because it's a 1 to 3. 4.5 moles of aluminium would react with 13.5 moles of magnesium. But we don't have 13.5 moles. There are only 12 moles in this particular reaction. So that's less than the 13.5 that are required. Therefore, this is limiting. Okay, on to part 3 then. Calculate the mass of magnesium formed. Well, you always lose the value for the limiting reactant, which in this case is the magnesium, 12 moles. And it's a 3 to 2 ratio. So if you have 12 moles of magnesium, that is going to be 12 divided by 3 is 4 times 2, 8 moles of aluminium. Then the moles can be multiplied by the relative formula mass of aluminium, which is 27, and that gives an answer of 216 grams. Part C is another definition. Water of crystallization, water that is chemically bonded into the crystal structure. How could you ensure that all of the water of crystallization was removed? Well, that's where you heat it to constant mass. And then calculate the loss in mass. So the loss in mass is going to be due to the loss in water of crystallization. So when this aluminium nitrate is heated, it'll thermally decompose into anhydrous aluminium nitrate and water. That's the equation for it. Now, if there are 1.5 grams of the hydrated salt, that's all of this. So we can work out the moles. So it's 1.5 divided by this RFM, that's 375. 0.004. Remember I said that the loss in mass is due to the loss in water of crystallization. Well, it's a 1 to 9 ratio. So the moles of water that are lost is going to be 0.004 times 9, which is 0.036. This then can be converted to a mass. So the mass of water, 0.036 times 18, which is 0.648 or 65 grams. Question 5 then, part A, is just a standard table where you have to fill in the number of subatomic particles, etc. Do be careful that you pay attention to here. These are atoms or ions. So we'll go along the first row. This is an atom, a lithium atom. The proton is going to be the same as the atomic number. To work out the neutrons, you subtract the atomic number from the mass number. Electrons is going to be the same as the protons because it's an atom, so it's 3. And then the electronic configuration is the number of electrons in each cell. Well, there are 3 electrons, it's going to be 2, 1. Next one is an ion. See, it's minus, it's a charge, so that means it's an ion. The atomic number is just the atomic number of fluorine, which is 9. Protons going to be 9. Neutrons, 10. That's all we need to do there. The next one then, the atomic number is 1. So that's going to be hydrogen. The number of protons, 1. Neutrons, 0, because it's 1 minus 1. Electrons will be, now be careful here, it's not 1, it's 2. Because the electron configuration is 2, that means there are 2 electrons. So then we need to go back to our symbol. It's not just H, because there are 2 electrons, 1 proton. It's got an extra negative charge. So that's going to be H minus. Calcium ion for the next one, atomic number is 20. It has to be because it's based on calcium. The mass number, well, you've got 20 plus 20. You add those 2 together to give you the mass number. It's 40. Protons, same as the atomic number. Electrons, now it's not 20. It would be 20 if it's an atom, but it's a calcium ion. And the 2 plus tells you it has lost 2 electrons. So that means there will be 18 electrons. And that's 2, 8, 8. Final one, atomic number 7. Okay, well, I know that's based on nitrogen. The electrons, I can see 10. Well, the atomic number tells me the protons, 7. I know there's an ion because it's got 7 protons, 10 electrons, got 3 extra negatives. That will be 3 minus. And then the mass number, just simply add the protons or the atomic number to the neutrons. That will give 14. And the final question then, calculate the relative atomic mass, give the answer to 1 decimal place. Okay, so don't lose the mark by giving it to 2 decimal places, for example. All you need to do is do 64 times 50, and then you add it to the 66 times 25, and add that to 68 times 25. You divide that by the total. There's a percentage, so this total will add up to 100. So sometimes it says relative abundance, so you still divide by the total, whatever the total added up to. That's 100, and that gives an answer of 65.6.